So I'll be talking about how this doing this octopole deformation doesn't solve the ultracentral puzzle, specifically with this relationship between V2 and V3. And so to kind of fully understand how we got to this puzzle, it's important to look at the history of the development of our understanding of the initial state. So the first step in looking at the initial state was just a first order approximation, thinking of the nucleus as a sphere. And so when you Lorentz contract these and then collide them, you get the initial state geometry appearing to mostly be coming from this overlap between the two nuclei. And so we classify these types of collisions using percent centrality, where the most central event or the most central collision in 0 to 10% centrality would be kind of head on. And so you'd kind of have a circular geometry. And then going to mid-central, you get a more off-center collision. And so this would have a more inherent ellipticity. And then in peripheral collisions, which would be like 80 to 100, you would have a much more elliptic shape. And so one of the ways we characterize this initial geometry, the main way, is using a Fourier decomposition of the initial state, where these epsilon n's characterize the different types of geometry present in this profile. So looking at the epsilon2 coefficient, if it's close to 0, you would have a very circular initial condition, where as it gets closer to 1, you'll be looking at something that's much more elliptic. So the way we quantify this is by doing a 2-particle correlation over many, many events. And the general trend that you would see in a plot like this is cartooned in the center, where for these central collisions, you'd have a value pretty close to 0. And then as you go out toward 60% centrality, you get a peak in ellipticity, and then there's kind of a drop off. This optical Glauber type model that is explained here doesn't really describe this drop off too much, but in all of the coming up plots, you'll see that this trend holds. So something really important that this model misses is that there's no triangularity. And this is a problem because we know that experiment measures a triangular flow harmonic. So there has to be some seed for that in the initial state. So the second order approximation to this initial state would be adding in nucleon fluctuations. And so one of the things this does is it enhances ellipticity. And so this just, instead of saying you have a smooth profile, your nucleons can fluctuate in position. And so in the plot on the right over here, you have these blue points, which don't have this fluctuation of nucleons. And then the red points contain these nucleon fluctuations, and then the black points are the experimental data. You see that including these fluctuations enhances V2 and gets closer to agreement with data, but there's still a shortfall here. There's also about a 10% effect on the number of participants when you include these nucleon fluctuations, because now you can have nucleons hiding behind each other, and you can increase the number of participating nucleons in the collision. This will also introduce a significant triangularity that I'll talk about more on the next slide. And this gives better agreement with the experiment, but there are still significant shortfalls here. So the next order approximation is to include multiplicity fluctuations. So this kind of emulates quantum fluctuations of gluon densities of the different nucleons. And so this allows the weight of each nucleon to fluctuate independently around 1. And so, yes.
Yeah, I'm just interested in what this Glauber really does. I mean, it's like two-body collision, right? So the Glauber is a two-body collision between. What is the Glauber? What is the Glauber calculus actually? So you see, in the Glauber calculation, in the nucleon context, with the nucleon scattering the nucleons. Okay, and my question is, what is Glauber in your context?
Can I help out?
Yeah.
Yes. I mean, so
Yeah.
take the Glauber density, the Glauber model density distribution for the nucleus, and then you use that as a probability density to sample the positions of the nucleons that fits with the fluctuating positions of the nucleons. And then nucleons collide with nucleons via two-body.
So if you did this kind of behavior in a heavy ion collision at much lower energies, then that would be basically the flow you would get would be the flow from collisions, which would be less than the flow from the observed experimentally, because there's a mean field. Now, I don't know what the concept of the mean field would be at these energies, but I'm just actually impressed that this kind of Glauber model gets you almost everything, rather than it doesn't give you everything.
Because the energetics is different, mean fields don't count in the energy levels.
Well, I mean, there are. Okay, so you say in the way that you're calculating.
So the flow is coming from after this.
What?
There's a response coming after you produce the initial condition, then you turn on the hydro to generate the flow. There's no flow at this moment.
Yeah, this Glauber model is just a way to
Just jump.
say what is the density, what is the density profile on the transverse plane, sort of at the beginning,
Okay,
and
so,
then what generates the actual.
but this geometry factor that we were seeing before, you're thinking that's all coming from initial state, nothing from the.
Yeah.
Nothing coming from the gluon dynamics.
Yeah, it's the hydrodynamic sort of evolution afterwards that's determines that the final flow you see is more or less proportional to these geometric eccentricities of the initial. But that part's not part of the Glauber model. That's the hydrodynamic expansion afterwards.
So, I mean, what Patrick is showing is that you have this overlap between them, and then you get this like almond shape basically from
Right,
this.
yeah. I get
And that's giving you the,
But how do you determine that it's inadequate?
well, you compare the data, right? Like at the end
But
of
the
the day.
data has all this dynamics in it that we're not talking about.
So Patrick's gonna get into that a lot more.
Yeah, and what the plot on the previous slide here is plotting the V2. So it's using an initial state with these different fluctuations, and then doing the hydro on top of that and seeing what the agreement with data will be. Yeah, so in the plot here, the blue curve is just including fluctuations of nucleon positions, and then the black and red are different parameterizations of including these multiplicity fluctuations. You see there's a significant enhancement of this triangular geometry. You can actually see in this plot here is displayed the ratio of the fluctuating or the eccentricities with the multiplicity fluctuations over the eccentricities with just the nucleon fluctuations. And you see for epsilon 2, which are the red circles, there isn't much of a difference up until like the most central events. But for all of the higher order coefficients, you have a significant effect across most centralities on the order of 10%. And so using both of these fluctuations, theoretical models can fit data very well, except at the most extreme regimes, which I'll talk about moving forward. So one of these models that works really well is Trento, which includes a model agnostic construction along with a Monte Carlo structure, and includes both the nucleon and multiplicity fluctuations. And so here are plotted VNs for both gold-gold and lead-lead collisions. And each of all of this data is using the same initial conditions from Trento, so the same initial states, and then running them through different hydro parameterizations, which would be the black, blue, and red curves. And then the black points are the experimental data. And so you can see that Trento is able to match a lot of the experimental data, except for the more peripheral centralities, where not all of the physics is present, and there's some mismatch there. And you can also see that they all appear to kind of, all of the different hydrodynamic parameterizations affect the initial state in a similar way. There's not too much disagreement between them, except at those more peripheral centrality classes.
Can I ask, this is not central to your point, I think, but I'm just curious. So these are different equations of state, right? Do you also adjust the viscosities?
Yes, I believe these would all have different viscosities, and both the equation of state is different and also the particle list. So the particle list is the same for the black and blue, but that would also be different for the red. So there might also be some difference generated from that.
So that's the particle list for the hadronic afterburn.
Yeah.
Yeah.
Okay.
So now looking at the most central collisions, so this is in 0 to 1% centrality in this plot. For ultracentral lead-lead, the theory orders V2 greater than V3, but the experiment shows that they should be about similar. So the experimental data is plotted in these green bands, and all of the points are different theoretical models. You can see that consistently all of them either overpredict V2 or underpredict V3. So this is a consistent inconsistency that kind of points to there being something more at play here, that our general models aren't being able to reproduce. On the side here, there are some references to papers and studies that have tried to solve this, but have been mostly unsuccessful. Another kind of tangential and kindred problem is the measurement of V44 to the 4th power, where in the purple band is the experimental data, and the blue points would be the theoretical data. And the experiment has this crossover at about 20% centrality, whereas the experiment has a crossover more around 40 to 50% centrality. So this is another area where our models are breaking down and not being, not in capturing all of the physics present. So now to kind of walk through how the hydrodynamic models get this ordering of V2 greater than V3, we first should think of this relationship between the initial state geometry and final state flow harmonics using this linear relationship where the kappa n is a response coefficient that contains the information about viscosity and the hydrodynamic evolution. So if we think of it this way, and also think about the initial state, in ultracentral collisions, your epsilon2 and epsilon3 should be about 0 because your initial state should be as spherical as possible. But when you include event by event fluctuations, you get non-zero values for both of these geometries. And then viscosity will order the response coefficients such that kappa 2 is larger than kappa 3. So hydro will kill off the higher order geometry more than the low order geometry. And so then this will lead to an ordering of V2 greater than V3. And so outside of the messing around with viscosity and the hydrodynamics, we want to try and offset the effect of viscosity by having an enhanced epsilon3 compared to the epsilon2. And so this might be a way to try and account for this mismatch and solve the puzzle. So one way of doing this would be optimizing triangularity. So we can do this by taking the deformed Wood-Saxon distribution and looking at the radius expansion and specifically the beta 3 parameter, where as you increase beta 3, you get a more triangular deformation to your nuclei. This would also affect your V2, but the hope is that it wouldn't affect it as much as it affects your triangularity. The values that we used for this analysis are taken from this other paper, which found that the lead 208 has preferable energy configurations with a beta 3 of 0.0375 and 0.075. We also used 0.12 as kind of an upper limit or bound. So the models we used in this.
Why are there two?
Yes.
Why are there two minima there?
I think it's different methods for calculating it.
Okay. Either one or the other. Or something in between.
Look like there's a lower energy state and higher energy state which prefer different beta 3.
So
Also, so the lower one is for the ground state, and that would be the unique value that's on that paper for the ground state.
I guess this all the mix.
yeah, this I actually saw the talk on Louise earlier this week. So basically, I think that the beta 3 with 0.037 is for the dynamical beta 3. I think the other one is possibly the static one, and then you have the excited stage, which is the 0.075. But we want to check a range of those. We know that as well.
The static one would be 0. Static one would be 0.
Yeah, the static would be 0.
So you're looking at that's not in the ground states for this experiment.
We were just trying things. So I mean, we tried originally 0.0375, and you'll see that it's not enough. So then we tried something longer.
So just reading
We don't
the,
want to say that people are adding that to the next slide.
I'm not saying that, no. I'm just saying that
There's a
that
motivation.
yeah, but that was motivation.
so the circles above are an odd parity projected state, and the squares
Oh,
down
okay.
below are even parity projected state.
I see. Okay.
So I guess the ground state should be the bottom one.
Okay. Okay. For checking.
So the models I'll be using for this analysis are the Trento initial state model, where we use both the reduced thickness functional form that came from their Bayesian analysis, which is this square root TATB, and the linear relationship that comes from more theory-based models, which is linear TATB. Moving forward,
Factors, what is it that scales with these factors, entropy or energy density?
yes, so the entropy densities found by Trento scales as square root TATB. The CGC models predict the energy density scaling as TATB. So there is also a little bit of a mismatch there. But for the rest of the talk, I won't talk too much about the linear TATB. That information is in the backup slides, but just for the sake of time, I took that out. And it doesn't add significantly to the story. So then we use two different hydrodynamic evolutions to look at what those effects would be. So for the first one is using this VUSP hydro code, which uses a state-of-the-art equation of state, or at the time, with a hadronic afterburner, which contains only full direct decays, but has a full particle list. And the bulk is set to 0, with the shear being constant. And then the music hydrodynamic code has a more outdated equation of state, but it has a full transport with URQMD, but it doesn't contain all resonances. It has shear and bulk that depend on temperature. So then looking at the two-particle correlation of epsilon2 and epsilon3, you see in the plot here, the black and red are using this square root TATB, and then the linear TATB is in blue and green. And then here, just to see kind of like the most extreme changes, are plotted the beta 3 equal to 0, and then the largest one we use, which is a beta 3 of 0.12. And you see that across most centrality classes, there is almost no visible effect from this beta 3 parameter. Although you can start to see some differences appearing at the most central points. And that's where we want to look at. So looking at that more in depth, we can plot the ratio. Yes.
We have about 8 minutes left before the questions session starts.
Oh, okay. So we can plot the ratio of epsilon2 to epsilon3. And the further this is below 1, the better. And so we see that indeed with increasing beta 3, you do get a better estimate of this relationship between epsilon 3 and 2. Another thing we can look at is the 4-particle to 2-particle cumulant or ratio, which, if you notice from this slide, these response coefficients kind of complicate things because they make it very hard to compare to experimental data. They aren't really, they contain a lot of information that can't be removed. But if you look at the ratio for similar coefficients, then you can kind of cancel out the linear response coefficients. And in the plot over here, we do see that you get this canceling out and it's more effective at the more central collisions. This ratio is also a good measure of the fluctuations of the specific geometry that you're looking at. And so here is the 4-particle to 2-particle ratio for epsilon 3. And this is plotted in relation to data from Atlas. And so you can see that there's an increase in fluctuations of your triangularity as you increase the beta 3 parameter, but it actually reduces agreement with the experimental data. So from this observable, you would prefer smaller beta 3s. So now looking at what hydro has an effect on with this V2 to V3 ratio, here are plotted both the spherical version and then the 0.075 beta 3 and the 0.12 for both VUSP hydro on the left and music on the right. And for VUSP hydro, it prefers the deformation, the smaller beta 3 deformation, whereas the music hydro code or hydrodynamic evolution prefers the larger beta 3 deformation.
I was also a bit confused because you mentioned several times in experiment they find larger P3 than P2 for ultracentral, but it's not very apparent from this plot.
So yes, so sorry.
Go ahead.
Restoration.
Yes, so the bottom of the axis is 1, and so this having a positive value means that your V2 is being overestimated in regards to your V3 by some amount.
But this is experiment. So this experiment says that V2 is bigger than V3 in 0.1.
Right. Sorry. So yes, the discrepancy comes from looking at the spherical lead. So without the deformation, you get an overestimate of this.
We're talking about Alice data, not the simulations. The data points that you are plotting say that V2 is larger than V3, which is different from what you told us in the beginning.
It's quite significantly so. It's like 4 sigma.
The issue is that V2 is basically equal to V3. It's not that it's actually negative.
It's a puzzle if you go through the data.
No, the puzzle is the theory. The puzzle is the theory to experimental comparison.
Anyway.
So that's the issue.
Okay, so looking at this a little more differentially and closely, if you look at the point-by-point view of these VNs for the music and VUSP hydro as compared to data, you see that there's an irregular behavior with respect to the beta 3. So it doesn't have a very clear effect on these VNs, which is a little irritating, but yeah. So then this kind of sums up everything in one plot. So along the x-axis is plotted V22 over V32. And then on the y-axis is the 4-particle to 2-particle ratio for the epsilon n, or epsilon 3 coefficient. And the green point here is experimental data with error bars. One of the caveats here is that Atlas and Alice don't report both of these observables, so we have to mix Though we have to mix them together to get this point. And then because the 4:2 particle ratio is a good estimate for the final state ratio, we use the initial state version of that for epsilon3, and then the final state V2 over V3. And so the blue points are using the music hydro evolution, and then the red points are using VUSP hydro. And as we increase the beta-3 deformation, we see a better agreement in the V2 over V3 ratio, but a worse agreement in the epsilon3,4 over epsilon3,2 ratio. So both of these have to be balanced when trying to further solve this puzzle. There's non-trivial interplay between those two observables. The current status of the puzzle can be summed up in a recent review, which utilized Bayesian models to show that this puzzle is still unsolved. So the gray band here is CMS data, and the points and yellow band here are all different theoretical models that can be said to agree at 1% centrality, but as you go to much smaller centrality classes, there is still this mismatch between experiment and theory. And so
you're being very unfair here, because this is figure of CMS, and exactly the same page on the left there is a figure of Alice, and there it works perfectly. So you just cherry picking here. Well, you're just cherry picking here the one which kind of says
The one that measures alter-center collisions, so you can actually trace out how did the models depend on centrality and how did the experiments depend on centrality. Every experiment has a V2 that just keeps decreasing linearly with reducing centrality, both CMS and Atlas, or CMS and Alice. And so this shows how this.
You have to compare, because Atlas is the only one that actually did V, or we're cheating, sorry, I was confusing. So Atlas is the only one that did V3 over V3,4, V3,2 with doing the error bars correctly. So everything else you have to do the error propagation on your own, you get massive error bars and so you have to do Atlas in order to look at V3,4 or V3,2. You could do either CMS or Alice when it comes to the ratio. It would be great if they actually did the cancellation of the error bars themselves for that too, because that you get larger systematic errors when you do this ratio. But unfortunately, I don't think any experiments have done that.
I heard a rumor that Alice is going to do more ultracentral bins, but I haven't seen it.
Let's go first. You see that the Alice ones that's kind of went through, and the CMS one not. And first here you show reactive, and we had some discussion about this. And we fit our data to Alice data, which has different cuts. So it's, I mean, of course, it's interesting to look at this. If you change the cuts, why it doesn't quite work well, and we should look into that. But it's, yeah, this is really an issue of like fitting to Alice and here changing to CMS rapidity coverage is much larger.
I mean,
I think this discussion needs to be a lot of experimentalists.
Yeah,
I
agree.
say it's very important to understand why they should do this.
Can I ask a stupid question? I mean, what happens is your collision occurs with the two slightly, the collision is not exactly aligned as you think it is. The beam has some divergence, and things do collide. They're not exactly equal and opposite momentum. They're close to it. How would you see that in this way? Sure, it shows a problem in the analysis of the moment.
So you're saying if the beams aren't completely head on, but come hit at an angle.
Well, it can't be a very big angle.
Yeah, so yeah, in reality, it's extremely small or large angle.
You know about crossing angle?
Yeah, the crossing
Yeah.
angle.
The beam spot, it happens on micrometer scale, whereas this the impact parameter is on femtometer.
So,
But the beam, how the beams are relatively clear.
So the beam crossing angle, but all the momenta are determined for physical detections, okay? And the axis of the event is determined by the beam. And my question is, if the axis of the event is not exactly along the physical axis of the detector, and you don't know it, what is it to these motions?
So I know in Greek, there, when they do Carzon, there's like a few milliradian, but I don't remember large hadron collider. I mean, most of you, I mean, in the rig, sometimes you have no Carzon, sometimes you put in some Carzon, because you want to narrow the beam, the Z vertex range.
Yeah.
But in LHC, I don't think they do the Carzon, I don't remember the deal, but because the beam is already very narrow, so there's no need to.
Well, I think that doesn't have anything to do with this plot, does it?
No, because I think he's not talking about just the crossing angle.
Yeah.
Because the beam is
Talking
there
about
with the
offset.
dispersion.
I'm just asking about what happens if the origin of your coordinate system, your axis of your coordinate system in your analysis is different than the actual axis of the coordinate system of the event, only by a very small amount. I mean, this is it's kind of just, it's probably just not an issue. But
Yeah, reality is negligible.
all of them here.
In principle, if it was a large angle, then you'd be, your different angles would be measuring different rapidities and.
Yanji, you want to?
But
A different question, so
Okay.
Yeah, I just wonder, how do we know, are we looking at the same event in the theoretical model and experimental? And I think this 0.1%, we're simply really, events which are very sensitive to fluctuation. And it is possible that, what you're looking at in the theoretical model is actually different from what we are looking at in the experiment. But we don't do any, resolution on folding on, anything. So, so that's something which we need to check whether the multiplicity distribution is reproduced and, all those things, right? So, so that we can move forward.
In fact, I mean, well, Patrick's not talking about here, but he's worked on like the tails of the multiplicity distribution.
There's a
And there's some issues there as well, so I think that could certainly.
Yeah, if you have certain central collisions, you have a certain fluctuation by that. Now, when you make this cut, you really constrict that quite a bit on the base space that you can allow for the event.
The point is that, the point is that each nucleon scattering you have wide fluctuation. Right? So we are simply probably some there will be the fluctuation already.
Okay, for instance, in this plot, but normally trajectory does it correctly. For instance, centrality, you do it in exactly the same way as experiment, just counting the number of particles with it from coverage. In this particular plot, I think I know that trajectory must change, and it actually counts the entropy and not the multiplicity. So then, and then it's a problem, because then if you look at 0.01% centrality, if you compare entropy versus multiplicity, there's big fluctuations and it doesn't necessarily agree. In this plot, luckily, you're still getting the right answer, because luckily this Vn doesn't depend on centrality. So even if you take the wrong events, because it doesn't depend on it, you still get the right answer. But that you only know by doing it correctly, which was done in our previous paper. So you have to be a bit careful, I think, for this.
We give the speaker a hand.
yeah, so let's can you wrap up, and then I guess we weren't in the question session yet.
Yeah, so I just wanted to end with a kind of question if nuclear structure could help with the solution to these inconsistencies. And then I just have my conclusions. So pretty much this puzzle isn't solved with this octopole deformation. And in order to solve this, you need to balance the effect on the V2 to V3 and the 4 to 2 particle ratios. And as far as this puzzle is concerned, this is still unsolved and a possible source of new physics and development.
We already had a bunch of questions. Maybe take.
More is coming back to what was said at the end during the long discussion. And the problem is really that you are diving into the tail of the multiplicities. And also that to trigger on this tail is not easy. So these experiments are not easily repeated. So the CMS analysis, I understand, will not be repeated because they can't implement that trigger anymore than they had at that On the other hand, I think what is needed is a much better understanding of these fluctuations and to see whether these fluctuations are correctly simulated in the simulations. I am not convinced they are. And without that, we will not be able to resolve that.
I just want to comment, we can read these essentially. And I think it's very important we provide ultracentral conditions using different centrality determination methods, and that will help us with the issue.
Yes,
That'd be great.
yes.
I think that it's super important in light of this workshop, because it's exactly the regime before we want to attribute a structure. So, you know, before maybe these fine details did not matter so much, but I think we're at the point now where they do matter.
It is possible that there are some nuclear structure input is missing, which is randomly without it.
If this is the centrality measured in a different rapidity range than these particles.
Yes.
So that's also missing, you know, the 2D.
Yeah.
Yes.
We don't have entropy.
So it would be very valuable to have what you described.
Right.
You have different centralities selections and different detectors.
Yeah.
You'd be interested, you know, then you can at least test that part.
That would have to have a model that has X dependence of the function.
Yeah.
But if you just experimentally, you could see whether there is a difference. If they select multiplicity in a totally different centrality and they see exactly the same result, then you know that it's not an important effect. So
I think we can.
it's not so bad that we don't have it in these models.
Does this imply when you're in all these analysis, do you have to introduce something which is kind of an odd parity perturbation of the and your initial point distribution here? I mean, I just don't know why you get this D3. It's very strange. I can more easily understand an even parity.
Finite statistics. You have a finite number of nucleons, you sample them, you analyze them in a Fourier expansion, you get a non-zero coefficient for the third harmonic. It's in the geometry. And then what Hydro does is converts this geometric deformation into a momentum deformation distribution.
Then you would expect to see some small moment for Harris.
Yes.
Yes.
Absolutely.
And why particularly would you feel that V2 should necessarily be bigger than V3?
Well, we try to compute where the geometry plus the fluctuation, so it's always the largest.
The point is that when you do this analysis with fluctuations, you find an ordering, and then you let the hydrodynamics react to that, and then you find this generic ordering that V2 is larger than V3. And the data didn't seem to agree with that until he suddenly showed the Alice data, which have V2 that's larger than V3. So I'm also confused there.
So just to be clear, like what he meant is that V2 is almost the same as V3. So it's not that V3 was larger ever. It's that in order to get the right relationship, because your kappas are smaller for V3, then you actually need a larger epsilon 3. And that then once you run through Hydro translates into a nearly equal V2 bigger.
Yes. The actual ratio depends on the cuts that you put in. So it's an oversimplified statement, but some measurements do have V3 larger than V2. Depends on the,
Yes,
especially the PT cuts.
In the plot that you first showed, CMS had clearly a V3 that was 0.05% centrality or something like that.
That was just 0 to 1% in that plot.
But when you put in so what you're doing is in these simulations, you're simulating the positions of the nucleons or simulating the positions of light?
Yes, the initial state, yes.
Yeah, I have the same question related to the why the nuclear structure and health. So this one, when we initialize the nucleons of the two colliding nuclei, doesn't the momentum distribution will kind of compensate things if you consider say polyvelocity? When you initialize the nucleons in phase space, you have say atom rate in coordinate space, when you have some kind of opposite effect from momentum distribution, will that affect the fluctuation from event to event? If you consider the initial momentum distribution. Right now, like all the nucleons are flowing without the initial flowing motion in the transverse direction.
So maybe we should give Patrick. Do you want to answer? Or?
I'm sorry, I couldn't hear that very well.
He was asking about, so when you sample the nucleons, they don't have any transverse momentum. But in reality, nucleons will have some amount. That'd be important.
Yes, that's my question, yes.
Possibly.
There's a sort of fluctuation from when to when, right?
I don't know that it might have an effect on when you calculate the initial state eccentricities, whether you say calculate them at right when Trento would like run, which would be like 0.6 Fermi after the collision, or if you have some like I guess some kind of pre-equilibrium evolution, which could be affected by the transverse momentum.
But this is not the transverse momentum of the nucleons in the nuclei before the collision. That momentum has an effect because the time that it takes for the nuclei to pass through each other is so short that the particles could have GeV momenta and not move anywhere in the transverse position. So you wouldn't see that. But after they have collided, the question is whether the momentum distribution of the stuff that is being generated, whether that has an anisotropic momentum distribution. And that's how people have studied and have found that any such an anisotropy in large systems like lead and lead is erased on a very short time scale. And what you see in the experiment is anisotropic momentum anisotropy generated by the geometry, not by the initial state.
Oh, okay.
So I think one way nuclear structure can happen, but that can help by providing, the correlated nucleon distribution. So we had a study where we actually used what Massimiliano calculates, where at least the two-body correlation that did make a difference for this prediction observable and potential. So if one can generate, these higher points or correlated distributions for that, it's of course hard.
Yeah.
But that might make a difference.
Is that in a paper? I don't remember
In
that.
this one paper that he showed that's still unpublished since 2014, but
Yeah.
Which input was it to?
I think it was that because we looked at the same data. I think.
Do you remember how big the effect was? Is that okay?
It wasn't quite enough. It went in the right direction though, right? So I'm just thinking there's probably a bunch of things.
Yeah.
We're so into the detail now, right? That everything matters at least.
Right,
in your
yeah.
initiative. So it's like maybe this HPT puzzle, right? Where you need a little bit of this, and a little bit of this until you get it right.
I mean, if you look, Pedro didn't quite mention, but if you look at the early results from it today, we've already gotten a lot better. In my paper, and the Gilbert also had papers on this, and I think it was more like a 20% or something. If I now it's on the order of like 10%.